Let's continue. Our next speaker is Honza Kral, Django contributor. He likes to be deep in construction and don't like to go to welcome.
Hello. So as it was said, my name is Honza Kral. I actually work for Elasticsearch, and I originally wanted to have a slightly different talk about what Elasticsearch is and how you can use it, but then I realized that for more people it's more useful to know actually how it works and what does it mean, so you can actually make that decision for yourself, understanding what are the trade-offs, what it can give you compared to other database systems. So I'll be talking about search in general, and not specifically about Elasticsearch, but generally how these sort of systems tend to work. In the areas where I had to choose one implementation, I went for Elasticsearch, so I use it as an example. But all this knowledge should be transferable. So let's get started. I said that I'll be talking about search, but unfortunately there is a lot of ambiguity what actually search means. So we need to start with a little bit of theory, or in what I conceive when I speak about search. So primarily for me, search is an interface to data. Whenever you have data and you want to expose them to the user, typically you do that through search. And either it's structured search, which is just filtering and sorting, or unstructured search, which is actually full text. So structured and unstructured, two different types. Structured is what you're used to from your SQL databases. That's the where clause and everything. And unstructured is what we'll try to discover here, how it actually works. So we'll use GitHub as one of the examples and how we can actually make this work. So we'll try our best to replicate this functionality in theory to discern how it works. So if you're given a task to find all documents about Django in real life or on a computer, if somebody asks you which books in your library actually mention Django. So the naive approach is you take out all the books, you read them all one by one, and you set aside those that actually mention Django. If those are not books but files on your computer, you do the same thing with grep. You just grep all the files for the word Django, and you get back the list of files. And finally, if it's models in your database or rows in your database, you just run an iContains query, which is a like query in SQL. And all of these have one thing in common. You really shouldn't do that. And the reasons for that are several. First, it takes a really long time to read all the books in your library, or to go through all the files, all the lines, and see for yourself, or to go for each and every record in your database and see if it accidentally contains this word or not. Those are very ineffective operations. That's one reason. And the second reason is they also don't give you the additional information that you expect. This approach doesn't give you the information which book concerns itself more with Django than with anything else. It doesn't sort the results in any meaningful way. It doesn't do relevancy. So, but surely this is not a new problem. Surely we must have solved this already. And indeed we have. In a monastery far, far away, in the year 1230, I'm sorry, I was a little pessimistic here. In the year 1230, a group of monks completed a concordance of the Bible, which means that they took all the important words and names and everything, wrote them down alphabetically somewhere, and for each of them list the passages of the Bible which actually concern those. So that was the world's first inverted index. in the world in the year 1230. So as you see, the theory for this is quite old. So how would that look in the modern day and age? Let's see an example of an inverted index here. We actually have a few documents that concern themselves with various subjects, and I've actually taken all the words that is in these documents and sorted them alphabetically. And then for each of them in the rows, I have the files which contain them. So Django is in file 2 and file 4, Flask is in file 3, and so on and so forth. So now, when I want to actually do a search, and I want to see all the files that concern itself with Python and Django, all I have to do is locate those two lines, take the lists that are at both of those two lines, and you can see that even the files are in sorted order. So I have two lists in sorted order, and I need to merge them and find the documents that are in both lists. So in this case, the result of the search Python and Django would be file 2. So, and that's all there is to it. This is the essence of full text search. We have sorted lists of terms, of words, and for each of those we have a sorted list of documents where it actually appears. And then when we do a search, we just locate the word, because that's on the input, that's what the user has given us. And then we take all the lists for all those words and we merge them, and we take the document. You can of course imagine that if I were to ask for Python or Django, I would just merge the two lists and take all of the files from there, not just the ones that are in both lists. So that's if I search for individual words. But oftentimes you want to do more. You want to, for example, search for phrases. So how would that work? And now we'll start with actually enhancing this data structure, this inverted index, to give us more information, more insight, and more functionality. So the first thing that we'll do is for each of the files that contain the word Python or web, we add the information in which position does this word occur. So we can see that with file 1, Python is the 4th word. In file 2 it's the 1st and 3rd, and so on and so forth. The web is here the 2nd word, and here is the 10th word. And what this allows us to do is, if we actually search for the phrase Python web, as in a Python web framework, we still have a very simple task. We have two sorted lists, but in this case we don't take out just the documents that occur in both of those lists. We also care that the offsets, that the positions need to be offset by 1. So we see 1 and 2, Python web, so we know that there is a phrase Python web. So again, a very simple operation to find a phrase. And you can immediately see that I could even say that I will allow certain words to be in between. For example, preposition or anything like that I don't really care about. And if they're in the middle of the two words, I still consider that a phrase. So I can even say that I'm okay with the difference between the two positions being 1 to 3. That's called a slot. So it enables me to do queries on phrases with a lot of free will to determine how the query should look and what's considered a phrase and what not. So this is another example of why this data structure is of the inverted index is very good for searching, because all we are always doing is merging sorted lists. And if any of you have programmed at all, which I hope that you all have, like you know that that's a pretty easy operation. Once you have two lists, it's very easy. Also, storing lists, is also pretty easy. So this is a very simple implementation that allows us to do a lot of things with the data. So this is how you use inverted index. We'll come back to it and add some more information, but for now, let's move on. Let's actually see how this magical data structure even came to be. So let's start with building the inverted index. First thing that we need to do is we take some text and then we split it into tokens. And you can see that I haven't just split it by words. I have done more things than that. First, everything is lowercase. Second, I skipped some words. Is, a, and. Those are words that are almost everywhere, at least in the English language. So there's no point in indexing them. They would just create noise. So I have a list of stop words, a list of words that are too common for me to care about. So I skipped those. And next thing that I did something that's called stemming. So for example, here you can see encourage, where the text actually say encourages. This is a way how to find the stem, the root of the word, so that when someone searches for encouraging instead of encourages or encouragement, it will always match. So it's sort of a way how to normalize any form of a word into one canonical format. And finally, the last thing that I did to this is I added synonyms. Because Django developers have very good vocabulary, and not necessarily everybody who searches for that will use the word rapid. Let's say that rapid is the same as fast, and let's actually index both of these as the same word. So in the inverted index, you would have both rapid and fast, and you would have the exact same lists for both of them. So it doesn't matter whether you search for rapid or for fast. It just will automatically match. There's nothing that you need to do. So to sum it up, this process is called analysis, and it's something that happens when you index a document, and it's typically you can of course customize it, and that's one of the critical parts that you need to care about when you're configuring your search engine. But by default, it will just drop the stop words. It will normalize the terms, the words. So it will do lowercasing, stemming. It will apply synonyms. For some other languages, it might do other things. For example, for a lot of the languages with alternate script, it will do Unicode normalization. For example, for Japanese, you need to take the two different scripts that they have and normalize it into one, which is a sort of a difficult problem, but somebody has probably already solved it. The important thing to remember about this, it happens at index time. When you index some document in there, this entire process occurs, and the inverted index is built. And once it's built, it's very hard to change. So I don't think that any of the search engines actually change it. When you want to change it, you need to re-index the document. So very important. The other important thing that you need to realize is that this process also applies to the queries, because otherwise it would make no sense. If I index encouragement and search for encouraging, I need to apply the same process to both to get the canonical version of both, so it will actually match. So this is how you build the inverted index. So we know how to build one. We know how to use it for searches, for Boolean searches, for phrase searches. But so far, I've promised you one thing that I haven't delivered. And that is, I said that we'll be able to search with relevancy. We'll be able to tell how well the document matches our query. And that's something that we can do. Because of the inverted index, we have all the information that we'll ever need. we have the list of all words in the entire data set. For each word, we also have all the documents that it's contained. And all that is left is a little bit of math. So this is a very complicated formula taken out of Lucy. Actually, it's not that complicated, but let's pretend that it is. And what it actually will do is it will take the frequency of the term in that field. So I'm searching for the word Django. So I'll take how many times does it occur in that document. That's the term frequency. Then I'll take the inverse document frequency. You can see I'm describing the middle, the TF-IDF. Inverse document frequency is how many documents also contain the word Django. And I'm taking these two values because they are important. Because if a document contains the word Django 5 times, but it's in every single document in our data set, it's not really that good a match, right? But if it's contained there twice, and it's only in 2 other documents in my entire data set, that constitutes a very good match. So I need both of these numbers. And the rest is just gravy. So for humans, it's actually like this. We take into account the rarity of the term, the number of occurrences, and also the length of the field. Because if I find Django twice in the title, and title is much smaller field than the body, let's say that we are indexing blog posts or books even, then the body would be a huge amount of text, and chances are that the word will be there more times. But it's actually more relevant if the term is in the shorter field, in the description or in the title. So that's also another thing that we take into account. So this is the TLDR version of the formula from the previous slide. So we have built the full text search. This is literally all you need. And there are some things that this gives you basically for free. For example, you notice that I was repeating over and over that we are just merging sorted sets. And you can realize, if you think about it a little bit, that it doesn't matter where these sorted sets come from. So we can actually have 3 different indices for 3 different fields. And we can search across. We can search for one field in the title, for one term in the title, for another term in the body, and still do the merging. We can even search across indices that don't even have the same document. I'll just get the documents from all the indices. I'll get their score, and then I'll just sort it by the score. So you see that there is a very little limitation in what you can do because of the simplicity. So that's why it's all built around the inverted index. But so far we've only built the small part of the search, albeit the most important one. But there's still a lot to do. The first thing that we'll add to this. So we only have the one input text, and then the list of results. That's okay. Like Google has been working with just that for quite a while, but they do a lot more behind the scenes. For our site or something, we want more functionality. So the first one would be highlighting. You can see, well, you probably can't, but you can imagine that when I search for something, I get all the occurrences of that highlighted. So when I search, in this case, I'm searching for job, and I'm finding all the Django repositories on GitHub. And you can see that even if I'm searching just for job, the entire Django book is actually highlighted. So how does this work? Because obviously it's not done on the front end, because like the 2 words have very little in similar. So how does this work? And again, we use the trick of enhancing the inverted index. So So where we previously had encourage, we now have encourage the same, but we also have the offset and length of the term in the original document. And not only that, we have the offset of the original term in its original form. So you can see 49 and 59, that's 10 letters. That was for the encourages. So this enables us to say that when I did a match on the encourage and it actually matched, and I want to do the highlight, I'll just take the numbers from the posting list, from the list of documents, and I can do the highlight without computing anything, without analyzing anything. I will insert the start of the highlight at the position 49 and the end of the highlight at the position 59. And you can see that it even works for synonyms, because you can see that rapid and fast have both the same offsets. So when you search for fast, the rapid word will get highlighted, because we just do the positions here, and we say that the original word for this term has been at the position 60 to 65. So we don't need to do anything. So that's how we do highlighting. Again, just add something to the inverted index and it makes it really easy. So that's one thing. The second thing that we need to add is the filtering and faceting. Faceting is a fancy word for aggregations. And what it does is, it gives you an overview of the data that you're getting back. For example, here, it's the same search, searching for job, and we have how many repositories it has found, how much code pages, issues, users, and we have the same for languages. We even have the count. It's sorted by the count, and there's even some visualization in terms of bars. So how does this actually work? So for the user, it works that you just define some buckets, and because any aggregation in any sort of database in any sort of way is always just define a bucket, and then you compute an aggregation on everything that falls into that bucket. So you can define bucket by term. So everything that has the same value in some field. For example, if you have a value in your document, if you have a field language on GitHub, so this will put all the documents that have Python in that field into one bucket, and all the documents that have JavaScript in that field into another bucket. And then you can do applications like count. So just using these two, you can see that you would get the languages, the lower one. So for each value of the language field, you get the count of the document. And that's all there really is to it. And we can do it fairly easily based on the inverted index, because all we need to do is de-invert it and then run the aggregation. So we just create another index from this one, which actually just maps documents to the values, and then we just iterate over it and compute the aggregation. So that's one use of the faceted navigation. That's the official term for this sort of interface. The other use for the facets is actually visualizations, because you can even define buckets per time period. So here you can see we have buckets per like 1 minute or something, and we have the values. We have a number of requests. This is a visualization of an Apache log. Here you can see the split between types that were requested. This is a terms facet. So here we can see that this one is PHP documents, this is HTML, and so on and so forth. even when we click on individual row, we can see that for this field, we have this distribution of values. So this is actually from an interface called Kibana, which is worked on top of Elasticsearch, and it's a pure JavaScript application. I'm mentioning that so that you know that this has all been calculated in Elasticsearch. The JavaScript in-browser application doesn't actually do heavy number crunching, surprisingly enough. So that's Facets. But facet navigation won't work without the other thing. What happens if you actually click on Python in that interface? It then needs to filter. And filtering is very similar to search, except we can cut some shortcuts. For example, with filtering, we don't really care about relevancy, because anything that doesn't match will not even be included. And we don't really care how well it matches, because everything will match the same. Because here we are filtering on exact values. No analysis, no splitting of terms or anything. We have one field, one value, and we want to filter. And again, that's something that we can do using the inverted index exactly the same as we did the full-text search. But because we can cut some corners, we get some nice benefits out of it. A, it's much faster because we don't have to calculate the score. We don't care about frequencies and anything like that. And also, it's actually cacheable. So together with facet navigation, with facets, this makes facet navigation, which makes a really good experience for your users. For example, if you search for products on Amazon, this is the thing that will give you which colors are available, so that it serves very well for discovery. When you didn't know what's in your dataset before, now you know because you have it there, and you can immediately click on red and see only the products that are actually red. Also, when used with the visualizations, with the analytics, it also gives you a nice way how to discover what's happening in your data, a nice way how to drill down. Because filters, for example, can also be range filters. So you can immediately limit your result set from yesterday to today. That's also a filter. So that's another piece of the puzzle that we put together. And the one last one that we'll attempt is the did you mean suggester. So when your user doesn't really know what they're looking for, they'll type how they think it's spelled, and more often than not they get it wrong, either because of a typo, and typos are very common. Like even some Django core contributors do typos a lot. No, I was getting our joke. No. Sorry, wrong audience. But not just because of the typos, but also because people don't remember how it's spelled. So when you do a misspelling, again, because of the inverted index, because we have lists of all the terms, of all the words that have occurred in the data set, we can find the similar words to the one that we've typed in. And if the similar word is more common than the word that we've actually typed in, so here I'm searching for Django. If I do a search for that, I find almost nothing. But I can see when I look up the word that's right next to it, and by next I mean an arcane measure called Levenstein distance, which is an edit distance. It's the number of edits that you need to do to a word to make it into another word. So in the neighborhood of this term, if I find something that actually occurs in the data set a lot more times, I am now confident that I can make suggestions. So it's based on the terms, and it will offer you the closest variant that actually is in the index. So this should be enough theory for now. We can go back more later. Now just how do I actually use this? So if I want to start using this from Python, if I have some documents that I want to index and search, all I need to do is this. So on top there is a very raw way how to actually do the queries using Elasticsearch. So you just import the client, you instantiate it, and then you do a search. You search over an index, or you can search across more of them, as we've discussed, or across all of them, and you supply the body. Here, I'm looking for the word Django in the title, and I'm getting back the terms facet for tags. So essentially, the distribution of tags in my data set. And this here is again the same thing, but using a new DSL library for Python that I've been working on. So this is how you actually use it. It's not hard. You don't have to write any arbitrary queries. There are just some dictionaries that you need to create, or use the DSL that will actually create the dictionaries for you. And if you want to actually get the data in, so imagine that you have a Django application. So you have some model. So you just iterate over all of them, pull 2 JSON on each, and then just feed it into like a helper function that comes with a client. And this will index all your models from all your instances of that one model. But that will just do the initial load. Then what you need to do is create a function like this and bind it to the post-save and post-save argument signals in Django. And this is literally all the glue code that you need to enable indexing all your Django models. Combined with this, which you would put into your view, this is all you need to implement a search for a Django application. So that's it for now. If you have any questions, I'll be happy to do the questions. And if we end up having some more time, we can go about looking into some more advanced topics. So we already have questions there in the back.
Hello, thank you for your presentation. Could you please show the slide where you are splitting the phrase and merging first and everything?
In this one?
Yes. So you split the phrase and you split it high and level. So I think you must do some kind of tokenizing here because high and level split it does not make any sense for user. And the question is, how are you doing this?
Good question. So it's always good to know that somebody's actually paying attention. Yes, by default, high level, a hyphenated word will be split into 2. But that is not such a big problem as you might think, because if you again search for a high level, it will get split the same. So even though it will not then find an exact match, and it might find something that has level was high as well, but it will still prefer this match. But if you actually have some knowledge about either the language or some business knowledge, you can actually define this yourself. So you can actually define that high hyphen level is one word and should be treated as one word. So that's where why I said that configuring the analysis process is the most important part, because of cases like this. So in this case, you can just say that high level is one word and it shouldn't be split, or nothing should be ever split by the hyphen, and do it like that. So it is a little bit of a problem, but not so much, because it will still work like this. If you search for high level, it will find this. That's one thing. Second, you can actually fiddle with it and fix it using the analysis process. Does it make sense?
Thank you for a good presentation lecture. It's very interesting to me because I made the same book some years ago. And I have a little question about the next frame, next slide, with inverted index structure. Oh, yeah.
Sorry. Yeah. This is perfect.
And another one question.
Sorry, Keynote crashed.
Okay.
This slide?
No. About reverse index structure. About information that lost in stemming, like a word form. Sometimes it's very useful for exact phrase lookup and stop words too. When users have a phrase consist at least of stop words and low relevance words that produce a lot of noise, and
yes.
Have a special fields about word form and something I like in reverse list.
So there are several ways how to do it without actually getting rid of the stop words. One way is we actually can do a query that's called a common terms query, which we'll not filter out the stop words, even not from the search and not from the document. But when we're actually doing the search, we'll split the words into two parts: the very common one and the not so common one. And we'll do the search first on the non-common one. And only in the resulting data set will we take into account the common one, the ones that we would typically split out. So that way you can do that. The other possibility is to just not use stop words. And typically what people do is they would analyze their data multiple ways. And when they're querying, they would query against multiple versions. So you would have one version analyzed without the stop words, one with the stop words, one not analyzed at all, taking it as verbatim value, and then when you search, you'll search across all three of these indices, and then the ones that will match the best will have matched in at least two categories or something like that. So that's another trick how to actually solve this.
Sometimes you need to do two requests similar in parallel and then select the best one.
No, you don't need to do this as a separate request. You will just do a query and you will instruct the query to search across these three variants, and it will be all in parts of one query, and it will happen automatically inside, and it will be completely transparent. You'll just get one set of results back.
And another question about misspelled words and about multivariant words. For example, about misspelled Django word. If these words arrive not in query but in text, what about to find user really don't know these words spelled correctly or not?
So the assumption in here, we are not making a judgment whether it's correctly or not. We are making a judgment whether it's in more documents than not. But also what you can do is when you query, you can again fiddle with the query a lot, and you can say that I want this query to be fuzzy, which means that it will not only match the terms, but it will also match the neighborhood of the terms using the Levenstein distance metric. So in that case, even if you search from Django and you have a misspelled word in your document, the document will still be found.
Thanks.
Thank you for really excellent information retrieval introduction. My question is about misspelled words. How can one really look up the next word by the Levenstein distance? I cannot imagine how I can build index for this.
So there are some assumptions that we make, and some heuristics that go into this. One of those is that typically if there is an error, it's typically not on the first letter. So, and because we sort everything in sorted order, everything that starts with the same letter will be next to each other. So then we can just scroll there and calculate the Lavenstein distances for the words that are fairly similar. And there are some very effective algorithms how to compute Lavenstein distance. So you can actually do that while iterating over the dictionary, over the list of words.
But if the word is very long and error is in second letter.
So that shouldn't really be a problem. I don't know what exact optimizations there are in Lucene to make this more effective, but also know that a lot of this also happens in parallel, because as I said, that the inverted index rarely changes, which means that typically when you index new documents, new inverted indices start to be created. So you're searching across not one but multiple. Then there's a backend process that will actually keep merging them into bigger ones. But essentially, this all happens in parallel.
I have an answer.
Thank you.
Another question?
Thanks for the presentation. I have one question, and it's it's not like total question, so bear with me. The problem is this: we have, for example, some documentation about some framework, and it's framework called, for example, Django. Yep. And this documentation has only one file, one page, where there is a lot of words Django. The Django is the framework, and so on, the definition, and etc. Then, somewhere in all those files, in all those documentation about this framework, we have like search, header, and it's talking about search functionality that's built in Django, for example. And if user now asks Django search, he would never ever find this in this kind of infrastructure, just because we don't operate higher levels of abstraction of text. We operate only in low levels. So there is no way, the whole document is about Django, but we never, but this kind of structure will never knew that, will never understand that. And what do you think about that? And maybe there's some ways to hack it.
So this is a situation where you have some business knowledge that the search engine cannot detect automatically, so you need to actually step in and do it yourself, either by removing the word Django from the data set, from the query. When this sort of thing happens, so somebody searches for Django search, and you know that you've only found things when you do just this naive search, you'll get back a lot of documents that mention Django, but not search. So you can actually know that, because you can actually ask the search engine to give you the information on which it based its selection. And then you can say, oh, hey, it didn't actually find the second word. Let's try searching just for the second word. So you can actually do this. Or you can even say that the search is required and the Django is optional, using the similar pattern that I described earlier for the stop words, the common terms. So you can say that Django is so common that you can safely ignore it and place emphasis on the second word. So there are different things that you can do, and you need to try it a little bit and see what will give you the best result. But you need to inform the search engine of your situation somehow. Okay. Any other questions? Going once? Going twice? Okay, thank you very much for having me.